Hi, my name's Will Krosick, Scientific Services Manager at Chemical Computing Group. Today I'd like to show you how to analyse a protein-peptide complex, and we'll do that by looking at key interactions and hotspots. Then I'll show you how we can use that information to optimise the design of our peptide. So let's get started. So I'm just going to go ahead and open the file that we're working on today. I select it in the Open panel, hit OK, and I'm greeted with this Load PDB file panel. This allows me to select what data we're going to load into Mo. And here I happen to know the structure we're working on contains a dimer, so for that reason I'll click on the Symmetry pull-down, select the biomolecule assembly, hit OK, and the monomer appears in the main Mo window. Note it's coloured by secondary structure, so helices in red, beta sheets in yellow, turns in blue. Next, what I'm going to do to get familiar with what we have in our system, I'll open the System Manager and pin that to the main Mo window. As the name suggests, this allows us to manage what we have in our system. From here, I can hide and show different atom sets, I can make selections, I can also render and generate surfaces. Note at this point that all we have in our system is receptor and solvent. Note that there's no ligand. I'm going to come back to that point in a moment, but next what I'd like to do is prepare this complex ready for interactive analysis. So for that I'll call upon QuickPrep, the panel comprising three main sections. The first handling preparation and cleanup of the structure, second sets tethers and restraints, the third handles refinement. I'm just going to make one change to this panel. I'll explain why in a moment. Hit OK. I see the calculations initiated and I get a progress update at the top left of the main Mo window. So I'm just going to go back to QuickPrep to explain what's going on and why I made that change. So the first stage of QuickPrep is preparation. It ensures we've got a complete model. Here we add missing hydrogens, charges and sidechains, and also building any missing loops. As part of this, we're also performing Proteinate 3D to optimize the ionization states of bound molecules and sidechains, and also generating a hydrogen bonding network. Next comes the tethers. So by default we tether our atoms, and that's applied to the receptor atoms. You can think of a tether like an elastic band. It allows the atom to move, but if it moves too far from the original geometry, the elastic band's going to pull it back to the original starting position. And this way we won't deviate too far from the original crystal structure geometries. Now the fix option is the one that I toggled off. Normally it allows us to fix any atoms 8 angstroms or further from a ligand, which is a good idea when I'm preparing a model with a ligand bound and I want to focus in on the binding pocket. In this case we don't have the ligand, so because I don't want to fix the entire structure, I need to toggle that one off. Next comes refinement, which performs an energy minimization to ensure that we don't have any clashes in our structure. So I notice QuickPrep's complete. The message has gone from the top left of the main Mo window, so I'm going to cancel that panel, and then I'm going to go back to the System Manager, and actually I'm going to change the view. I'm going to change from the basic view to extended, and when I do that, notice that we've got two entries for receptor. One relates to the receptor, MDMX, and the second one relates to the peptide, so this is P53. And what I'm going to do at this stage is I'm going to ask Mo to consider this to be our ligand. So if I click on ligand on the right hand side button bar, I'm going to opt to call that our ligand, so choose ligand. And notice the System Manager's updated, we now have a ligand entry together with the receptor. Next, I'm going to hit Site View, so that's going to isolate our ligand together with any residue within 4.5 angstroms, and then what I'll do is I'll use our System Manager to render the system to our liking. So we'll make the receptor orange. I'm going to choose to hide the solvent and I'll make it inert. Note the I representing inert in the System Manager. I'll display the ribbon on our peptide, and then I'm going to colour our peptide a bright colour. I'll make that cyan so it's easy to stand out. So with that we've set the rendering, we've prepared our model, we've rendered it to our liking, and next what we can do is familiarise ourselves with the interaction between peptide and receptor, and based on that analysis we'll see if we can optimise our peptide design. So note here that Mo has automatically calculated and annotated the classical hydrogen bonds, and they're shown by these dotted lines with a cylinder in the middle. And the cylinders here give us an idea about the strength of the bond. So the longer the cylinder, the stronger the bond. If I want to quantify that, I can use the bond rendering tool to display the bond strength in kilocalories per mole. Click it twice to display the bond length in Armstrongs, or just a plain dotted line. I'm just going to cycle back around to my preferred view of the cylinders. So here we're looking at the classical hydrogen bonds, but Mo can also calculate non-standard interactions such as proton-pi, halogen and sulfur interactions. So here, looking at the complex, I see that we've got a good hydrogen bond on the N-terminus of the peptide. I see lots of intra-peptide bonds, and if I just rotate our model around, I see that we also have a good hydrogen bond on the C-terminus. If I'm interested to see what residue we're interacting with, I can click on the residue and I get a readout on the footer here. So here we're looking at lysine in position 47. But perhaps I'm less interested about specific residues and I want to build a picture of all of the interacting residues. For that, I'm going to generate a ligand interaction diagram. So this generates a 2D schematic of our ligand and the interacting residues. There's a key at the bottom that helps us understand what we're looking at here, but in brief, these green residues represent those that are greasy or hydrophobic. The pink or purple residues indicate that those residues are polar. If I just make this a little bigger so it's easier to see, I'll draw your attention to the dotted line here. So this represents the binding pocket, and in this case our ligand, our peptide, is surface bound, but we can see that some of these residues here are quite well buried. The blue cloud indicates that the ligand's exposed to solvent, so we can see some of these residues are certainly exposed to solvent, and in contrast we see some of them are buried. Also note the hydrophobic interaction. So this 2D diagram is a good place to start to understand a complex and the scope that we might have to optimize our peptide design. But we can go a step further by having a look at that in 3D. So I'm just going to close our ligand interaction diagram, and next I'm going to generate some surfaces. So I'm going to start with a receptor surface which is colored by atom type. Predominantly orange because we set the carbon atoms of our receptor to be orange, but we can also pick out blues and reds corresponding to the nitrogens and the oxygens. Now this particular surface type is useful to identify hydrogen bonding opportunities, and we can identify those by either cyan or white patches. Here's a good example of a white patch representing a polar hydrogen. In this case the peptide has already utilized that hydrogen bonding opportunity, but in contrast, if I have a look around our complex here, I see lots of cyan patches. Cyan represents the lone pairs, and we can see that there's quite a few running along this groove, so these are perhaps opportunities for hydrogen bonding that we could modify our peptide. So what I'm going to do at this stage is I'm just going to label a couple of our residues so that we can come back to these that coincide with where the cyan patches are located on the receptors. So I'll just go ahead and select a few of these, and I'll opt to display the residue label on those. Now I can display different properties on this surface. So as an example, if I click on the receptor surface and the color pull down, you'll see some of the properties that we can display here. So for example, lipophilicity. So this allows me to identify the greasy or hydrophobic regions of this binding pocket shown in green versus the polar regions shown in pink or in purple. So we can see our peptide sits in this hydrophobic groove. So already we're building a good picture of the interaction between peptide and receptor. So we're getting an idea about where to optimize our ligand, but the question then becomes how. What mutations are going to be required and where would we like to see them? And fortunately, Mo has some tools that can help us with that. So for this I can call upon electrostatic maps, which I can find within the Surfaces and Maps menu. This is the main control for all molecular surfaces created by Mo. The panel's split into three. We get a list of any surfaces we've already created. The second part allows us to generate new surfaces, and the third section allows us to edit. I'm just going to move that to one side, and I'll hide our receptor surface. And next what I'm going to do is generate an electrostatic map. So this is going to generate interaction hotspots and give us information about the receptor, not the peptide. It tells us where the receptor would like to see an interaction, and it tells us what type of interaction the receptor is looking for. So this is all useful information when we come to optimize our peptide. In the main Mo window, we can see white, red, and blue hotspots corresponding to hydrophobic, acceptor, and donor. So let's go through these one at a time, starting with our white hydrophobic patches. So I can see we've got quite a small hydrophobic patch here, and this is perhaps a good opportunity to use this slider so that I can better understand the origin of that hotspot. So if I just use this slider, I can see here that corresponds to the hydrophobic groove that we saw earlier. And in this case, we can see that the peptide is satisfying that interaction. It's touching the hotspot, it's got the right type of interaction, which tells us there's nothing we can do here to optimize the design of the peptide. So with that, I'm going to toggle off hydrophobic hotspots and move on to look at the acceptor hotspots. So here I can see that we've got two main acceptor hotspots. One of these we already identified acting on the terminus. We can see there's already good hydrogen bonds, so this acceptor has been utilized. But conversely, I see we've got another acceptor here. It sits next to our leucine, but there's no hydrogen bond between the receptor and our peptide. So this is a potential opportunity to be able to optimize our peptide design and pick up an interaction with that red acceptor hotspot. Let's move on. I'll toggle off the acceptor and then have a look at the donors. So again, I can see we've got quite a few donors here. One of them acting on the terminus, again with that strong H bond, well utilized by the existing peptide design. But conversely, I see we've got quite a few that run along the groove that we saw earlier. Another one next to what happens to be another leucine. So again, another opportunity to be able to optimize the peptide here for an interaction with a donor this time. So at this stage, I think we can say that the analysis of the complex is complete. Just to recap, we use the receptor surface to identify the lone pairs and the potential hydrogen bonds, and then we use the electrostatic maps to identify both an unsatisfied acceptor and donor hotspot. So with that, we're now ready to use that information to optimize our peptide. I think our strategy here should be to leave those strong bonds that we saw at the termini alone, and we'll preserve those because there's already a good interaction. I think we can leave the hydrophobic interactions that we see buried here alone. They seem to be working well, but we'll build for better interaction with the acceptor hotspot and a better interaction with the donor. So I'm just going to toggle off our hotspot, and before I start modifying our peptide, I'm going to duplicate it. It's always a good idea to make a copy so that I can refer back to the original structure. So I'll right click on the ligand entry, click duplicate, and you'll notice now we get a second entry in our system manager. The original peptide coloured in cyan is set to inert, so that's not going to be considered in any calculation. So we're now working on the grey copy. I'll just opt to display the ribbon. I'm also going to give this a bright colour, perhaps we'll make that magenta, and then I'm going to adjust our hydrogens display. So this works like a toggle switch. I click it once to display all hydrogens, click it twice for no hydrogens, and then a third time to get to my preferred view of the polar hydrogens. Now, as we come to modify this ligand, we're going to want to keep track of its properties. So for that, I'll toggle on the ligand properties displayed in the top left of the main Mo window. These describe bioavailability. So we've got a prediction on toxicity, molecular weight, TPSA, and so forth. And these are updated on the fly. They reflect any changes we make to our peptide in real time, so we can keep an eye on these to ensure that the peptide we design is also bioavailable. Next, what I'm going to do is hit minimize. So that relaxes our peptide in the binding pocket, and the reason I'm doing this is it allows us to calculate these 3 additional properties: strain, solvation, and affinity. I'll just give a quick mention to affinity, a measure of how well the peptide is interacting with the receptor. It's an energy, so the more negative that value becomes, the better the interaction. And again, we can keep track of these properties as we make modification, but note that these last 3 are only updated every time I hit minimize. Next, I'm going to call upon our builder, and I'm going to pin that to the main Mo window. This is our small molecule builder, but if I click on the builder pull down, you see some of the different builders that we have within Mo. Today, I'm going to be using the peptide builder, which has a list of the standard amino acids at the top. I've got some non-natural amino acids, and I have options here to customize my own should I wish. The middle section of the panel allows me to explore conformations and minimize, and the bottom allows exploration of rotamers. So what I'm going to do next is just toggle on the acceptor hotspot, and I'm going to build for an interaction here on this leucine. So if I just go ahead and select the leucine, note that it becomes highlighted in the protein builder panel in blue, and note that our panel is set to mutate mode rather than prepend or append. So I'm going to want to change this leucine for something that's charged, and for that reason a glutamic acid comes to mind. So I'll just go ahead and make that change. And note, as soon as I do that, the residue is changed in real time, and we've straight away picked up a H bond, which is reassuring. Next, though, what I need to do is just model this for the local environment. So one workflow here would be to repack. So that repacks the sidechain with the environment fixed to find the lowest rotamer energy. And then what I'm going to do is minimize. I'm going to minimize the selected sidechain only. And then I'll actually perform a global minimization as well, just to recalculate my strain, solvation, and affinity. And I see we've got a slight gain in terms of affinity there. I see that we've picked up the H bond, so I'm happy with the modification that we made there, and I'm going to move on to look at our donor hotspot. So here, what I'm going to do is select the leucine. Again, it becomes selected. And I'm going to want to change this for a charged lysine in this case. Now, it's added the group, but it's not necessarily in the position that I wanted. And I have control here to be able to manually modify this. So I'm just going to use the bond rotation tool, and notice as I get close to that donor hotspot, I'm picking up a H bond, which is good to see. That's one way to manually change the placement of the sidechain, but another option that I'd have is to use our dihedral plot. Here we've got our bond rotation on the X and energy on the Y. This solid white line is showing me the energy within the binding pocket. The vertical green line shows me the current angle, which also happens to be at the energy minima. The dashed line shows me the energy of our peptide in the absence of the protein environment. Now, these blue bars leverage a program called Mogul, which is performing statistical analysis of similar crystal structures, and it's telling us here that the typical angle we'd expect to see is plus or minus 180. Now, in this case, we do find a few examples at the angle that we've set of roughly minus 4.5, but what I'm going to do is perform an energy minimization to allow Mo to just allow that peptide and the receptor to relax. And we see here that we've got a good hydrogen bond and a suitable increase in terms of affinity. So again, I'm quite happy with the modification that we made there. So at this point, what I'm going to do is I'm going to bring back our original crystal structure of the peptide, so shown in cyan, just to allow us to compare those two. So here I can see that we've been able to retain the H bond at either terminus. We've been able to retain the original hydrophobic interactions deep in the core, but we've picked up these additional interactions on the 2 leucines. So we've got one over here, which corresponds, perhaps it makes sense if I just toggle on our acceptor and our donor hotspots. You see that we picked up that additional interaction on the donor, and if I zoom into our leucine here as well, which doesn't have the interaction, our glutamic acid in contrast does. So that brings us to the end of today's session, where today we saw how to analyze a protein-peptide complex using the right-hand side button bar. We did that by looking at key interactions and hotspots, and then we used that information to optimize the design of our peptide. I hope you've learned a lot today. If you have any questions, please do reach out to us at support@chemcomp.com.